So this is Intro to Stats Week 2. First off, we're going to review some of the stuff that we did in Week 1. So that is 1 and 2 variable data is what we looked at last time. So with 1 variable data, we talked about the difference between categorical variables and quantitative variables. Categorical variables are things that can be described by qualities like ice cream flavor or favorite color. And quantitative variables are just pure numbers like test scores or age or height. And then we looked at how to describe quantitative distributions. So we use the acronym SOC-V. These are the things that you need to touch on when you're describing a distribution. That's shape, outliers, center, variation. That's what SOC-V stands for, is shape, outliers, center, variation. Then we looked at population versus sample, and therefore parameter versus statistic, because any piece of information about a population is a parameter, and the same about a sample is a statistic. So a sample is just a subdivision of a population that you're going to take information and study, because a population is the entire thing and is usually too big to study. And then we looked at the normal distribution, which we said is important for sampling and is determined entirely by its mean and standard deviation. We're going to go more in depth into that one probably next week. With 2 variable data, we talked about 2 categorical variables and how we can display those. Those are mosaic plots, bar graphs, or if we want to just have the raw data without a graphical representation, we can put it in a contingency table. We also looked at 2 quantitative variables, also known as bivariate data, which can be displayed in scatter plots most of the time. And we went a little bit further with that and said that we could trace the scatter plots with something called the least squares regression line, which is also what you might know as the line of best fit. And we can test the appropriateness of the model of least squares regression with residual plots. And then finally, we looked at outliers and influential points, noting that the distance from the least squares regression line is what determines an outlier, and the distance from the center of the line is what determines an influential point. So that is what we did in week 1. Oh, here is a quick review of some of the formulas. So I know this may look intimidating. You don't really need to know it, but this is the correlation coefficient R. That's the formula for that. This is a formula right here for a least squares regression line, with this being R. S of Y is right here, the sample standard deviation. So the standard deviation of the Y values. S of X is the same thing for the X values. X bar is the sample mean, and Y bar is the mean of the Y values. And this, I don't want you to be intimidated by this symbol. It's the capital sigma, a Greek letter, and it really just means the sum of everything that comes after it. So here, this isn't something super complicated. It means you take this and you add them together. So that is what we did on week 1. Now we are going to move on to week 2, which is data collection and probability. If anyone has any questions, you can feel free to put them into the chat or ask me, just unmute your microphone and say it out loud. So with data collection, first we need to note that collecting data is vital for drawing conclusions. We can't just guess, right? We can't just say something. We have to collect data and then use that to make a conclusion about something that we are interested in. So it can be faulty. Data collection is not always perfect, and there are a couple precautions that we can take to try to minimize the error, but we have to take those precautions, otherwise our data will be meaningless. And some of those precautions are listed here: randomization and sufficient sample size. What that means is the samples that we take, they have to be large enough to where we can draw meaningful conclusions, and they have to be randomly selected. So we can't just go around picking whoever we like. We have to choose it randomly. There are two different ways to collect data. That's experiments and studies. So experiments, we will get to those later. Studies we'll start looking at now, specifically observational studies. Two types of observational studies. Retrospective studies examine existing data. So that means data that's already been collected, usually for a different purpose than what you're looking at it for. That is a retrospective study if you're examining that. So advantages of it are it's cheaper, quicker, and easier, usually pretty small scale. But it is reliant on memory, so it's subject to memory bias. Then it also could be subject to faulty record keeping. It's less controlled. You can't really influence what you're keeping track of. And the data is gathered for other purposes, which means you might not know all of the variables that you want to. On the other hand, prospective observational studies, they monitor data that you are currently collecting, which means data that is happening now, being taken right now, or will be taken in the future. That is what prospective observational studies look at. These are usually more accurate and you can keep track of exactly which variables you want to, but it is expensive and more time consuming. So it takes more effort, but if you can, go for prospective. Now we are going to look at bias. So bias is something that can really throw off any conclusion that you draw. The only way to completely get rid of it is if you take a census, which is a sample of the entire population, but that is practically impossible to do. For example, if you're going to take a census of all adults in the United States, you have to ask whatever question you're asking to every single adult in the United States, which is not practical. So you have to settle for sampling, and sampling methods can largely be biased. So some ways to identify sampling methods bias is if in some critical way they consistently result in samples that do not represent the population. That's a textbook definition of bias for a sampling method. Types of bias are listed here. There is voluntary response bias, which is choosing only the people that want to participate. For example, if you say, anyone can call in and tell me your opinion on this, that would lead to voluntary response bias because only the people that call in are going to give you their answers. And that leads to you only getting the strong opinions because people that don't really feel strongly about whatever issue you're discussing, they are not likely to call in. Then there is convenience sampling bias, which is choosing only those who are easily accessible. Like if you go to a mall and you just ask everyone that walks by, that is a convenient sample for you, but it is not really representative of the population. That's tied closely to undercoverage bias, which is just any sample that is not representative of the population. For example, if you survey people over a phone call, it's not representative of those who do not have phones. Then there's response bias, which is where people don't want to answer honestly, and that could be caused by a variety of factors. This includes not wanting to be judged, holding an unpopular opinion, not wanting to admit to something incriminating like having a criminal record, something along those lines, but it leads you to have inaccurate data. Then there's quota sampling bias, which is it's good intentions, but it never works. So that is if you try to pick people from different groups to make your sample representative, that is an absolute recipe for disaster. Just trust the randomness. Take a random sample. Do not try to pick a representative sample. That will not work. That is quota sampling bias. And then there is question wording or order bias, which is when questions are worded in a way that it leads to one specific answer being preferred. Like if you ask a yes or no question and you word the question so that saying yes would seem offensive, that would be an example of order bias or question wording bias. So to eliminate bias the best we can, we use different types of sampling methods, and they have different advantages and are used in different situations. So these sampling methods, the main ones that we're going to look at are, first, the most basic, a simple random sample. This is when you mix all of the members of a population and you randomly select them. This can be done just assigning each a number, then using a random number generator, and you pick each member corresponding to the number that was selected. And then there's a stratified sample. So the way stratified samples work is you take the population and you split it into strata, which are groups based on a common characteristic. And then you take a simple random sample from within each stratum. Important thing here is that the strata have to be selected based on some common characteristic. That's what separates it from cluster sampling, which is when you randomly split the population into clusters, and then you take every member of some of those clusters. That's illustrated in this image here. When in the stratified random sampling, they are split into strata based on their color, red or blue, and then some members of each stratum are sampled. Whereas with cluster sampling, they are split into random clusters regardless of their color, and then the entire clusters are sampled. And finally, there is systematic sampling, which is randomly ordering a population and then choosing every kth member. K can be any number, it's a variable. But what that means, or what that would look like, is if you take a sample, take a large number of people, assign each one of them a number, and then you randomly mix up the order of the numbers, and say for every third person, you would select them. So if there were 50 people and you wanted to take a systematic sample of them, what you would do is assign each person a number 1 through 50. And then for every kth member, let's say K is 3, you would take every third member. So you would look at member number 3, member number 6, member number 9, member number 12, and so on, until you get as many numbers as you can. That is a systematic sample. Next, sampling variability. This is first thing we want to look at is precision versus accuracy. So a common misconception is that they are the same thing. That's not true. So precision is how close the sample statistics are to each other. So if you run multiple trials and then you get a mean, you get means that are really close to each other, that is precise. Accuracy is how close they are to the population parameter. So if you, let's say you take multiple samples of adults in the United States to try to figure out the mean height of every adult in the United States, and the mean heights of your samples are close to the actual mean height of the population, that's accurate. But if the mean heights of your samples are just close to each other, that's precise. And it can be both. We are hoping that it's both, but there are situations where it is one or the other. So this is an arrow board analogy, right? So here, these ones are precise, but they're not accurate because they're all close together, but they're not close to the center. Here, they are accurate, but not too precise because they are kind of spread apart, but they're all close to the center. And sampling variability, it can result in even an unbiased sample giving unrepresentative results. So it's not the same thing as bias. Bias is a systematic error. That means that something in your system is going to sway the results. But sampling variability is just something that we can't get rid of. It's in the nature of sampling because we can't ask everyone. So the chances are it's going to be slightly unrepresentative of the population that we want. That we can't get rid of. It's not a flaw in your system. Experiments are the next thing. These are not the same as observational studies because they first off control variables and create the data on their own rather than observing it. And this is an important thing. They can establish causal relation. They can do this because they try to eliminate the confounding variables, which are variables that we're not trying to test that could have an impact on what we're looking at. So an example of an observational study would be looking at, say, SAT scores from the past year. That would be a retrospective observational study. Whereas experiments would be, an experiment for a similar purpose would be taking a group of students, testing their SAT scores before, and then putting them through a course, and then testing their SAT scores after. So now you know that the scores changed because of the training that you put them through, and you do your best to eliminate all other variables that could change their SAT score, like extracurricular tutoring or something like that. That's why you can establish causal relation. So you may have heard of something called correlation does not equal or imply causation, right? And that can be exemplified by this image here, because ice cream and sunburn have a correlation. The rates of ice cream consumption go up at the same time the rate of sunburn goes up. But that does not imply causation between the two, because it is not as though eating ice cream causes sunburn. It's that they both happen to be more common in the summer, because hot weather makes you want to eat ice cream, but it also makes sunburn more likely. So these two are just correlated, but there is not a causal relationship between the two, because they're both caused by a confounding variable. But in experiments, you try and eliminate the confounding variables, so then you can establish a causal relationship. That's the main difference between an experiment and an observational study. So here is some experimental vocabulary that's good to know. First, we have an explanatory variable, or a factor. This is what you might know as the independent variable. That's the variable that is controlled by the researcher. Then the response variable is a variable observed by the researcher in response to the explanatory variable. So if we were to stick to that SAT example, right, the presence of training, whether the students have been trained and have studied or not, that would be the explanatory variable that's controlled by the researcher. And the response variable would be the score that they get, either before or after the training. Then confounding variables, or anything confounding, means when the impact of undetected external factors cannot be distinguished from that of the explanatory variable. So what that means is you can't tell if the difference in the response variable is caused by your explanatory variable that you're testing, or a confounding variable, something from outside of your experiment, and you can't tell what that is. If you can't identify which is causing the change in the response variable, that is confounding. And then you have a control group, which is something to test for confounding variables, which basically means that the group is not given treatment, or it is given the current treatment if you're trying to test that new treatment has an improvement over the current treatment, or it's given a fake treatment, a placebo that has no impact. And that is to test if there will be a difference between the control group, which is given no treatment or a fake treatment, and your actual experimental group, which is given the treatment that you were testing. Then there's this interesting concept called the placebo effect, which is where if you're given a treatment that doesn't have any impact, you still may respond in the way that you're supposed to, just because your brain is tricked by thinking that it had the treatment. There's this interesting video that people took an energy drink that was supposed to make them stronger, and then they actually could lift more weight after, except the energy drink was just colored water. But since they believed that it would make them stronger, their mind tricked them into actually being a little bit stronger. That was a placebo effect. So they test for that by giving a control group a placebo, which is a fake treatment with no actual effect. And if the control group's response variable does not change, but it does in the experimental group, then they know that the change in the response variable is caused by the thing that we're actually testing. Next is blinding, which is when subjects do not know which treatment they're receiving. That can help eliminate the placebo effect, right? So they don't know if they're getting plain water or they're getting this magical energy drink that makes you stronger. That can help eliminate this placebo effect because they're just going to do what they feel. Finally, there is double blinding, which is where neither the subjects nor the evaluators, the response evaluators, know which treatment the subjects are receiving. So that functions the same way as blinding, except the people who are recording the results are also not biased. A little note here is that on a graph, if you were to plot the results of an experiment, the explanatory variable would be on the bottom on the x-axis, and the response variable is on the y-axis, because you're saying that the response variable is caused by the explanatory variable. All right, we're going to look at a couple of different designs for experiments. So the first is the most simple. It's the equivalent of a simple random sample, but for an experiment. This is a completely randomized design, which means subjects are just randomly assigned to whichever treatment. And there's no real system to it whatsoever. It's just everyone is assigned randomly to whatever. Next is a matched pairs design. The SAT example that I was talking about earlier, that would be an example of a matched pairs experiment. So that is when paired subjects, which is often the same subject just at different times, they receive two paired treatments, one each. This, like I said, often the same subject, but with each treatment administers at different times. So what that means is, as we go back to the SAT example, the paired subjects would be the student before the preparatory class and after the preparatory class. And the treatment would be receiving the preparatory class and not receiving the preparatory class. Next, there's a block design, which is the experimental equivalent of stratification or a stratified sample. Because the subjects are divided into blocks based on a characteristic, which is the exact same as how they would be divided into samples, into strata in sampling. The difference is now instead of being sampled from there, they're randomly assigned treatments within the block because we are collecting the data. We're creating the data in an experiment. So a block design is when you take a group of people, you divide them into blocks based on a characteristic, and then you assign treatments within the block. All right, so that is it for the data collection part. And now we have probability. This we're going to be going a lot more in depth into in next week as we look at probability, the second part, and sampling distributions. But for now, we'll just get to an introduction to probability. So first off, there is the law of large numbers. So a relative frequency of an outcome, the relative frequency of an outcome is just how many times that outcome occurs out of all of the trials, or the percentage of the total trials that yielded that outcome. For example, if you're flipping a coin 20 times, the relative frequency of the outcome being heads is just the number of times out of 20 that the coin was heads divided by 20. So if 10 times it was heads, that means the relative frequency was 0.5. Now, the law of large numbers states that probability equals a long run relative frequency. This is a hugely important concept for statistics, and it has implications that we will look into next week and further. Now, what this formula means is that as more trials are performed, the relative frequency of an outcome gets closer to the true probability of that outcome. So if we're going to look further into that coin flip example, if you flip a coin 2 times, it should be 1 heads and 1 tails, right? If it's 50-50. But that's not always the case because the law of large numbers does not apply to the number 2. What the law of large numbers says is that as you flip hundreds of thousands of coins, the proportion of heads that you get is going to get closer and closer to 1/2, because that is a true probability of getting heads. All right, so here are some basic probability rules. You don't need to memorize these yet, but at some point, they'll be good to know. So first off, we have the complement rule, which basically means that the probability of event A happening, the probability of event A not happening, is 1 minus the probability of event A happening. Or the probability of event A happening is 1 minus the probability of event A not happening. So for a coin, right, the probability of getting tails is 1 minus the probability of not getting tails. Then here are the multiplication rules. This is for dependent probability, which means if the outcome of event A influences the outcome of event B, then they're dependent on each other. In that case, the probability of both A and B happening is equal to the probability of A times the probability of B given A. That is, if we know A is going to happen, what is the probability of B? That's what this is. You multiply that by the probability of A, and you have the probability of them both. If they're independent, which means that the probability of B happening does not change based on the probability of A happening, or whether or not A happens, then we just multiply the two together. That is called the product rule. Is if they're independent, we just multiply the probability of A together with the probability of B, and we get the probability of both of them happening. Then if they're mutually exclusive, which means that B cannot happen if A happens, the probability of both of them happening, by definition, is 0. Think of it as two Venn diagrams. If they have no middle ground, they're mutually exclusive, then what's the probability that you land in that middle ground? None, because there is no middle ground. All right, here are the addition rules, which are the union of events. So the probability of A or B happening is probability of A plus the probability of B minus the probability of them both. So if we go back to that Venn diagram, think of the two intersecting circles right here. That would be the probability of landing in this circle or this circle minus the probability of landing in the middle. Then if they're mutually exclusive, which means the circles don't intersect, we're out here, then we don't have to subtract the probability of landing in the middle because there is no middle. So now we can just add the probability of A and the probability of B. Finally, we have conditional probability, which is the probability of A given B. If we know that B is going to happen, then what is the probability of A happening? And that is the probability of both of them happening divided by the probability of just B. And finally, we have my favorite, the Bayes theorem. This is the probability of A given B equals the probability of B given A times the probability of A, all divided by the probability of B. So let me just go over what these signs mean. A apostrophe means A not happening. So this thing right here, that means the probability of A not happening. This, where we have the upside down U, kind of looks like an N, that means the probability of both of them happening, A and B. The N means and. Then this line here, that means given. So if we know that A is going to happen, what is the probability of B happening? And finally, this U here means or. So what is the probability of either A or B happening? And so last thing we're going to look at before we go to the Kahoot